everyone. We are now going to talk about a project that brings together several OpenMined contributors, the PGTPFL demo project. We agree this title is full of anachronism. It's not very explicit about the content of the project. In 30 words, our project is to work on a proof of concept where the use of differential privacy associated with federated learning could enable the development of a model that respects both patient data privacy and the data sovereignty of healthcare. For this proof of concept, we therefore had to choose a use case, and here's how it can be stated. An hospital would like to have an estimate of the length of stay for each new patient admission. In fact, about 10 hospitals have the intuition that the data from previous hospitalization could be used to develop a model that would make it possible to predict the length of stay, especially if the model could learn from the data of all these hospitals. Unfortunately, hospitals have some constraints, and we cannot do that. They don't want the data to go outside of their premises, and they would like to have a guarantee that the model has learned a general trend and not a specific data from a few patients. Indeed, patients' data are very, very confidential. Several excellent studies have already shown that classically trained machine learning models can perform well on this type of predicting length of stay. In order to carry out our project, we have chosen to represent the results of one of these previous work in order to have reference results to which we can compare ourselves. For this baseline, we wanted that the medical data could be accessible by all our contributors to have a simple neural network. No LSTM, no CNN, for example, as a first step. With regard to the data, the MIT Lab for Computational Physiology made an openly available dataset comprising the identified health data associated with about 6,000 intensive care unit admission, including demographic, vital sign, laboratory tests, medication, and more. If you are interested, you can find a lot of additional details on this database called, as you can guess, we will use data for the Mimic3 database, but no, all of it. As for the model itself, we are focused on the model proposed in this paper. As you can see, this paper is a benchmark, so it proposes much more than the model we have chosen. We want to reproduce the fit-for-network architecture on the database, which is an extract from the Mimic3, which I called FeederSeed-C.
As you can see, there is a very strong motivation behind distributed learning. There is a large number of requirements, such as data has to stay private, the model has to have a high utility, potentially institutional anonymity, standardized learning setting, etc. However, as you see from this slide, when we meet the reality, it's very difficult to obtain those, primarily due to the fact that increasing the utility of the model can come at the cost of user privacy and vice versa. Consequently, those two are very difficult to balance out, which is what this project is all about. The existing solution to the distributed learning is just using a centralized server where the data is sent to the aggregate server. All the training is done there. The model is then distributed back to the clients. While there is a slight downside of using this approach, which is using too much data and having to send all this data to and from the central server, the main issue is there is no guarantee of privacy, which is why we decided to make use of the second approach, which is called federated learning. This method is designed to train a collaborative learning model without sharing the data with all other clients in the central server, in a setting where the aggregation server is primarily used as an aggregator, not as a learning node. We train the model on the local data, so the central model is generated and distributed across all three clients in this case. Then they compute their own model update and they share it back with the central server, where the model updates, so not the individual data points, are aggregated. The reason we think that this approach is much more suitable for our learning task is because, firstly, we only share model updates, not the individual data points. Secondly, it allows us to apply multiple privacy-preserving techniques on top of using federated learning.
Now that we got an idea of how distributed training is achieved using federated learning, we take a look at how to preserve the privacy of the hospital data using a technique known as differential privacy. Differential privacy is a smart way of adding random noise to highly sensitive user data to make it more accessible to applications while ensuring the privacy of the users at the ease of computation and minimal loss of utility. So as you see in the graph on the right side, It is a way of ensuring that we get the same big picture. At the same time, we're able to mask individual contributions. So the question is, how is DP achieved? We add random noise, which is sampled from a noise distribution, such as a Gaussian or a Laplacian distribution, and the shape and size of that distribution is determined by two factors: the privacy budget and the query sensitivity. So now we look at the application that we're interested in, that is deep learning. Deep learning is a way where we take input data from users and we apply a neural network recipe for prediction on top of it. And this recipe includes multiple important factors such as a model, which consists of its architecture and weights, a chosen loss function over which we try to minimize the loss value using some sort of optimizer. And our goal is that the network doesn't memorize the data, it should be able to generalize over the data. So now, when we want to add noise to this pipeline to make it differentially private, the question is, where do we add it? We could be adding it to the input data, we could be adding it to the weights of the model that we're training, we could be adding it to the loss function, or we could be adding it to the step of the optimizer. So let us look at a simple algorithm called differentially private stochastic gradient descent, which is a variant of stochastic gradient descent. So SGD is a simple optimization protocol where we divide the data into small batches known as mini batches. We average the loss gradient that's computed over the entire batch. And then we update the model using this average loss gradient. And we do so by taking a step in a direction that's opposite to the direction of the largest gradient. So now, if we have to look at a differentially private version of this optimization, the few changes that are going to be introduced is the first one is that when we are created mini batches, we will be clipping the L2 norm of those loss gradients before we average them. And after we average them, we would be adding Gaussian noise to be able to protect the privacy of the users. And finally, the update step would be the same, except that now the step taken would be in a direction opposite of the average noisy gradient. Using this, we are able to make the entire deep learning pipeline differentially private.
Now that we got an idea of federated learning and differential privacy, let's talk about how we can combine these two mechanisms to the existing PySift library. Our problem formulation has 3 steps. First, we build a deep learning model with DP guarantees that predicts the length of stay for each hospital admission. Next, we apply this model to predict the length of stay of a patient based on clinical data. And finally, we add a new tensor in PySift that supports DP-SGD embedded in an FL scheme inside PySift. Our proposed methodology has 2 major steps. First is data preprocessing. As mentioned earlier, we are using MIMIC3 dataset, which is a large single-center dataset containing clinical information of patients admitted to critical care units. We go through some preprocessing steps as discussed in the paper by Sanjay et al. And finally obtain the feature set C, which is a process subset of the original dataset. Next, we do some model implementation. At this stage, we implement 3 different models. First, we implement a simple baseline neural network without DP and FL. Next, we implement a simple network with DP mechanism. And finally, we implement a simple network with federated learning. At the final stage, we embed the DP mechanism to the federated learning based neural network through secure aggregation scheme. Now let's talk about how we can complexify the use case and develop necessary additional features. So our additional features include implementing dropout, batch norm, early stopping from a DP standpoint. Next, the use of a deeper network in order to analyze a potential correlation between the number of hyperparameters and corresponding model performance. Also, the use of more complex neural networks such as LSTM, CNN, etc. We can also analyze the impact of adding different DP noises to data. And finally, we can check how the model performance is going if we replace the trusted aggregator with a non-trusted one. Finally, I would like to thank all the collaborators from OpenMined who have been directly and indirectly helping in this project. You can contact us directly through openmind.slack.com for any questions and feedback. Thank you.